Thank you. I'm glad to be here to talk about a couple of papers that one of them is going to appear in the IEEE proceedings, special issue on big data, and another one we put on archive just a few months ago, involving large-scale search for correlations in this sample-starved situation where we have many fewer samples than we have variables, and for which, therefore, the standard computational algorithms, maximum likelihood, model-based statistical algorithms for estimating correlation or inverse correlation matrices are inapplicable, and because of computational complexity, and where the central limit theorem is not applicable either, because we're in this regime of fixed number of samples and very, very large dimensions. So I'm going to talk about this in the context of correlation mining, as it's called. I'm just going to give a little bit of context for the types of applications and procedures for correlation mining that have motivated this work. Then I'm going to talk a little bit about the high-dimensional analysis that we've been engaged in for the past 6 or 7 years in this problem, and then sample complexity, which will characterize the intrinsic difficulty of correlation mining in terms of the required number of samples in order to perform specific tasks, such as detection of a correlation within the matrix, sample correlation matrix, all the way to estimation of entries in that matrix. And then we're going to go to a two-stage sampling prediction adaptive regression by correlation screening, which we call SPARCS, which is a method which is motivated directly from this large p small n analysis for mining the correlations that enter into prediction coefficients of a predictor, a linear predictor, and then I'll talk about a couple of applications, some of which motivated this work. So this is primarily work that has come out of a collaboration with Bala Rajaratnam in the Department of Statistics and Environmental Earth Sciences at Stanford, and then a former student of mine, Hamid Farizi, who's now gone to the financial quant side of the world in Goldman Sachs, and sponsored by several sponsors listed here. All right, so correlation mining, in as far as it involves detecting large correlations among very high-dimensional data sets like mRNA gene expression. We have lots and lots of genes, genes on this axis, and a few measurements, or in email networks of spammers, or personalized social data for recommender systems, social collaborative retrieval networks, and so forth, involve several types of constraints on the acquisition of the data, the cost of acquiring that data, the value of the information that's extracted from the data relative to the particular task, whether it be tracking a target, if you're talking about forming correlations that go into a Kalman tracker, or constructing a network, a gene regulation network, if you're looking for molecular pathways from mRNA gene expression under different treatments. And of course, there's an issue of extracting features and then performing the correlation mining with error control, which is the critical issue here, is being able to ensure that in these particular tasks of detection, estimation of strengths of correlation, or a topology estimation, that we end up with repeatable results that are validatable and reproducible up to some false positive probability. And of course, that use domain information to control the errors. So this is sort of the general picture of some of the motivations that motivated us to look at the fundamental limits in the large correlation sampling regime that will limit the value of information per sample, or the sample complexity, as related to probability of detection error, probability of reconstruction error, of the support set of the correlation matrix, or the inverse correlation matrix if you're in partial correlation networks, or estimation of the correlation values. So, this is really the canonical big data problem, in the sense that there are a very large number of unknowns, large number of variables. There are perhaps hubs that you're looking for in a network, or edges, or number of subgraphs, which of course is exponentially large in the number of variables. There are a very small number of samples relative to the number of variables, and therefore there's a crucial need to manage the uncertainty due to sample variation, and all within the context of scalability. The problem, of course, is ubiquitous and very severe. There have been many papers that have come out in the past 5 or 6 years that have gone so far as to question the very basis of statistical methodology in high-impact research. One paper in particular, published by 2 statisticians here at UNC, appeared in Significance, basically reviewed the literature and came up with 12 different papers in very high-impact journals like the Journal of the American Medical Association or New England Journal of Medicine, where none of the claims in those papers were reproduced, and many of them reproduced in negative direction. And so this lack of reproducibility they claim, is due to either insufficient sample size, insufficient handling of uncertainty, and poor use of sample correlation, sample statistics. So this is a real problem, the problem of determining when one can reliably depend upon results, either results of declaring an association between a set of variables that indicates that, say, beta-carotene is highly associated with positive correlation to the reduction of susceptibility to late-stage lung cancer. So there's, of course, a wide background to this problem where you can, of course, be focused on covariance estimation or inverse covariance estimation, graphical model selection, which is basically topology estimation for the resultant network that comes from thresholding the inverse covariance or the covariance matrix of the population, testing for independence or testing for dependency within a large number of variables, or correlation screening, which is just basically testing whether there exists a large correlation in some set of variables that you might have measured, and then you might, then if you do detect correlation at a significance level which is appropriate, you go in and start to work up this list, then testing for dependencies between particular variables to trying to estimate the total topology, up to estimation, and maybe even further to trying to establish the uncertainty or p-values or the quantiles of the distribution of your estimates of these covariances. So what distinguishes the work I'm going to discuss from this work, the top ones here, is that we're dealing specifically with a case where the number of variables is much larger than the number of samples. So you can't depend upon the central limit theorem or models such as Gaussian models for the analysis. So I'll start here by talking about the particular model that we assume for the theory that I'll present, which is going to establish a large piece, a fixed-end limit for discovery of correlations in a very large sample correlation matrix, or a pseudo-inverse correlation matrix. And so we start out with a measurement matrix, which is populated with p variables along the rows and n independent samples along the columns, and that then creates a set of IID samples, right? N IID samples. If you subtract the translation parameter mu from the samples and form the outer product of one of these columns, you get the covariance matrix, which we're going to assume is sparse. And there are several notions of sparsity that we're going to, there are two notions of sparsity we're going to make use of here. One is just general row sparsity, so the maximum number of non-zero elements in a given row is bounded by little op, and block sparsity, where there is some permutation of the rows and columns of sigma or the inverse of the covariance, sigma inverse, which renders this covariance matrix block diagonal. And so we're looking now at the correlation matrix, which is simply the normalized covariance, normalized so that all of the elements are between -1 and +1, which now has an adjacency matrix, which is simply obtained by counting or thresholding out all of the 0 elements in this sparse correlation matrix. So you apply a threshold with rho here equals 0. The rho is the threshold, the correlation threshold you will apply. And then you can talk about estimating the support set, which is basically finding the rows whose sum is greater than 1, the hub degree support set, or finding the number of rows that, for which the sum of the non-zero elements is greater than delta. So this is equivalently the degree of a particular node in this graph, right? So the assumptions we're going to impose on x are very loose. We're going to assume that there are the columns of x follow an elliptically contoured distribution. And so you can construct the p by p sample covariance matrix, which is going to have rank n minus 1, where n, of course, here is much less than p. And then the sample estimator of the adjacency matrix is obtained from the correlation matrix, the sample correlation matrix, by thresholding at some level rho, where rho is now this threshold that has to be chosen. So the question is, how do you choose that threshold in order to ensure a reliable set of edges, right, in the graph that comes from your adjacency matrix, or that ensures that your estimate of the support set, that is the topology of this correlation or inverse correlation graph, is close to the true topology. So that then denotes this process. We select a threshold. We apply it to this correlation matrix with entries between -1 and +1. We get an adjacency matrix. That then maps directly to a correlation graph. And then we can talk about 4 different tasks. One is a correlation screening, simply detecting whether there are any rows at a particular correlation threshold row which have a number greater than 0 of 1s, right? So that have edges in the correlation graph. Support recovery, we're looking basically at the probability of classification error of any edges is an error relative to the truth. S0 is the true topology. S hat 0 rho is the topology obtained by thresholding this correlation matrix at level rho. And then covariance estimation through Frobenius norm. And finally, uncertainty quantification, which is estimation of the estimator tail probabilities, where the estimator is sigma hat. So there are lots of asymptotic regimes that have been looked at in the context of correlation estimation and correlation models. The classical regime, which is the central limit regime, which I characterize as the small data application, is when n goes to infinity, p is fixed, and there's lots of work on this problem going way back to Roland Fisher's original work earlier last century. Mixed asymptotics have been very active area where you have n and p going both to infinity at different relative rates, which is applicable to the case where you have medium-sized data, and purely high-dimensional regime, which we're focusing on here, is when the number of samples is fixed and p goes to infinity. So we argue that this is really the the realm of exascale type of data where you don't have the luxury of allowing n to get large in an unbounded fashion. So the point here is it's important to design whatever procedure you're going to design for whatever sampling regime is prevailing, because samples cost money and the number of variables may be extremely large. So the problem that we're facing is one of phase transitions in the estimates of the correlations that exceed a given threshold. So let's say we choose a threshold for, in this case, we have an IID set of Gaussian variables. So there are no edges in this graph. None of the correlations are real. And so any correlation you detect, so any value of this histogram greater than 0, other than a correlation equal to 0, is a false positive. And if you start to reduce the number of samples successively so that you become as few as 1/10 of the total number of variables, you're effectively in a very squeezed area where the all of your positives are false positives, right? So these critical thresholds are things that we've derived in our previous work under these assumptions of elliptically contoured sparse covariance models. And this just shows the degree of accuracy of these critical thresholds in this particular case of in this case, a Gaussian IID process. The threshold is interesting because it tells you that this threshold creeps up to 1 relatively slowly if n is large, because p to the power 1 over n minus 1 over n is approximately log of p, right, for large n. But if n is fixed and p is very large, this can run up to 1 very quickly and squeeze you in a very bad way. So we have a theorem that on which this is related or based, where we have a Poisson type of limit on the number of false discoveries of hubs of degree delta for a particular threshold rho applied either to the sample covariance or the sample inverse covariance, where, again, we use the Penrose pseudo-inverse to estimate the inverse covariance. This is like a Poisson limit, where this lambda parameter is the rate of the Poisson variable. And that rate, in the case where you have a block sparse covariance, not a row sparse covariance, with a row sparse covariance, these results are correct. But for a block sparse covariance, it turns out that this J function, which is the only place where the actual correlation comes in, that J function is equal to 1 when you're block sparse. And p goes to infinity. And so effectively, the false positive probability is independent in the block sparse case of the true underlying distribution. So it's a universal limit. So this allows us to set family-wise error rates. For example, if you wanted to set up the threshold to detect hubs with a particular level of error control, right? This is just simply the beta function, which is closed form. And again, delta is the desired hub degree that you want to detect in the graph. And so this shows sort of the blessing as opposed to the curse of dimensionality, where if we have an increase in the threshold, the critical threshold, which is actually quite favorable as a function of the number of observations. In other words, it increases relatively slowly, even for very large p. And so here's an example where, if, let's say you want to detect hubs of degree delta. Here delta is equal to 1, so we're just trying to look at connectivity for the blue lines up here. And let's say we're looking at a 0.7 is the minimum level of connectivity that you're willing to accept. Then if you have 10,000 samples, 10,000 variables, so it's your correlation matrix is 10,000 by 10,000, you only require on the order of 50 or 60 samples, right, to obtain that level of performance. On the other hand, if you increase to 10 billion variables, so 6 orders of magnitude increase in the number of variables, you only require roughly twice the number of samples, right? So 1 order of magnitude increase in the number of samples accommodates 6 orders of magnitude increase in the number of variables. So this is a very nice fortuitous behavior, which of course is related directly to the fact that we're in this very limited sample starved regime, this purely high dimensional regime. As n gets larger, things get not as favorable, right? And this just shows the same plot in a different way. So if you're looking, say, for, again, 0.7, this is the number of observations that you need as a function of the number of variables going up to 10 billion. So all of this is in our paper in the IEEE Proceedings, which is about to appear. And so one now can compare the results that I showed in the theorem in terms of the regime for which you maintain a fixed detection probability if you're doing detection or screening, a fixed classification error probability in support detection, a fixed Frobenius norm mean squared error if you're doing estimation, or a fixed density estimation error if you're trying to do quantile estimation. And so what you can see is in these regimes, if you go from the most simple operation, which is detection, all you want to do is to detect whether or not there is correlation in a large number of variables, you're in a regime where log p over n basically has to go to a constant, right, as p gets large. And so that means that n only has to increase as log p. In the case where you're looking for recovering the entire topology, then n has to go linearly in p to infinity. If you're looking at parameter estimation, you have p log p as the number of required samples. And then for quantile estimation, for characterizing the actual performance, you have an exponential requirement on the number of samples as a function of p. So you go all the way from a logarithmic complexity to an exponential complexity in terms of the number of samples. So that's the sample complexity analysis, which effectively says that from left to right, you require progressively larger sample size. So what this suggests strongly is the recommendation for multi-stage type procedures that progressively use samples to pare down the more complex tasks in sequence. So this shows a picture of that cartoon. If you have a sample size that increases in this direction, and you're looking for just simply screening for any correlations in your sample, then you can start screening for a very small sample size, and then as you screen, you then can go to support recovery and estimation progressively down the line. So for budget-limited applications, this is a very useful concept, as I'm going to illustrate with this two-stage sampling prediction adaptive regression via correlation screening type of paradigm. So let's say we have an experiment that we're designing, but we have a finite budget, right? And we can, in this particular case, I'm looking at a regression problem where we're trying to predict a response. In this case, it's a symptom response using a molecular set of probes in terms of a gene expression. So these are your independent variables. And you can do a lot of these experiments. Now, you can either spend all your money to buy very large chips that have all the entire genome processed on the chip, all 12,000 or 22,000, depending upon your normalization procedure on the chip, and then you'll have a limited number of samples. However, what you could do is apply this correlation screening for the first few samples where you know we're in that logarithmic regime. You only need log of p samples to pick out those particular probes, those genes, that are highly probable to correspond to edges in your graph, your correlation graph, and then use the rest of your money to buy samples which are much less expensive that only contain those genes that pass the test. And then you continue this on if you wanted to, say, do estimation of the quantiles of this particular of a particular edge, let's say. So we call this, as I say, sparks. And the predictive correlation screening is not simply doing screening on the correlation. If you read this paper, we do screening on the pseudo-inverse correlation times the cross-correlation vector. And so it's a generalization of Schur independent screening by Fan and Loeb. So we have a theorem that basically states that we have a sample complexity which is on the order of log p in terms of predicting this variable y using this multi-stage procedure. And I don't have time to go into it, but we have an analogous condition for this support recovery guarantee that you can recover with probably at least 1 over 1 minus p, the support of these active variables in the regression. We then have the more interesting consequence of this is that if you have a budget of mu, let's say, and let's say you're going to select a number k of variables, so you'll apply a threshold so that you select exactly k variables, and you have a total number of samples t. So to meet the budget, you have in your initial stage of n samples where you're going to sample the entire genome, right? You'll have n times p, where p is the size of the genome, and then you'll use the k samples, the k variables out of the genome that pass the test, and you'll use the rest of your t minus n samples for that. So you get this this constraint. So the theorem says that the number of samples you should allocate for your initial first stage screening is only on the order of log of t. So this makes a lot of sense because detection, we know that the detection is a function of the number of samples, that the detection probability decreases exponentially fast, whereas the estimation probability, which is what actually we're trying to minimize in terms of the mean squared error, decreases only 1 over n, right? So that's where you get this log t. But it says you have to allocate relatively few samples to the screening. So I'll just conclude here with a couple of examples. Flu challenge experiment where we're looking actually at predicting a symptom response, where we have a set of time points and a set of subjects where you apply inoculation at some time 0. And before that inoculation time, we have a bunch of so-called baseline samples. We have 16 subjects here. We have on the order of 18 time samples. And then some of the subjects got sick. Some of the subjects got sick down here. Some of them did not get sick. And we can divide this into basically 4 different regions. And these were all published in various places by us and our team here at Duke, in fact. The samples fall into these categories. Pre-inoculation samples, there are 34 samples total. We can calculate, using the theory I gave you, the critical threshold is 0.7. So that's the minimum correlation we should be confident about. And if we're worried about a positive of 10 to the minus 6, then that correlation false positive threshold is 0.92. So any correlation that we putatively find that's less than 0.92, we can take with a grain of salt. And then you can go through these other cases and find their appropriate thresholds. So one interesting result that we have, if you just look at the pre-inoculation samples, these 32 samples, if you screen the correlation, you get a very large and complicated graph. If you screen the partial correlation at the same level of false positive, you find these 4 different modules, and one of these modules corresponds to a sentinel immune response that is sitting just waiting to be recruited once an inoculation occurs, which has a very high correlation and at 0.92 or greater, because that's how we've set the false positive threshold. And then this just shows the Sparks comparison as compared to Schur independent screening and Lasso. Lasso is a single-stage procedure. SIR-independent screening is a two-stage procedure that simply applies the screening to the correlation as opposed to the correlation pre-multiplied by the pseudo-inverse. And our proposed method much more quickly in N exploits the value of the sample so that you obtain a much lower misclassification rate and also a lower average mean squared error in the predictor. So in conclusion, this asymptotic regime, this purely high-dimensional regime, is, I think, a very important one where n can remain fixed while p goes to infinity, and then you can talk just about detection of a very high level of correlation. These are universal, they're universal phase transition thresholds that occur that are independent of the correlation, the true correlation, if you have a block sparsity condition, and then you can use these for properly sampling, sample sizing some experiments. And we haven't covered some other applications of this, which I won't talk about here because I've run out of time. But you can take a look at these references which I've listed here. So thank you.
Questions for Al? So I'll give us a chance, and we'll have the next speaker set up while we're waiting. So I have a question.
Yeah.
In fact, if you go back one slide. So in the gene, or a couple slides, in the gene example,
yeah.
So you're essentially looking for large correlations between the symptoms and some gene.
Yeah.
I didn't understand exactly what that was in terms. It was like the symptoms were cold or flu, right?
Right. So here you're trying to actually predict. It's not so much correlations between the systems, the symptoms and the independent variables that you're interested in. It's actual accurate prediction. So the optimal predictor, the ordinary least squares predictor, of course, depends upon the correlation through its inverse and the cross correlation between the symptom and the independent variables. So where this theory came in was estimating that that inverse, that pseudo inverse, or inverse of the correlation, right? So that we derived the theorem directly in that context.